So we've talked about what happens when we try to take statistics from a population. It's often impossible. It isn't very easy to do, and it's really expensive. And so we're going to talk about what happens when we take samples from the population. So if you could take all the different possible samples, and the samples are the same size, and it's taken from the same population, and you take all the possible samples, and you found a statistic for each of these samples. Most of the time it's the mean, but it could be something like the proportion. And we create a distribution from all of these sample statistics. So if we could take all the possible samples and they were the same size and we took it from the same population and we found a statistic for each sample, we're going to talk about finding the mean today, but it could be proportion. And we create a distribution with all of our sample statistics or all of our means. There are a number of different things that can happen. There are different things that can happen. So if our parent population or the big population is normal, then when we take a sample of any size, then the sample distribution, the distribution of all our sample means in this case, they're also going to be normally distributed. It doesn't matter what size our samples are, they are going to be normally distributed regardless. First of all, if the parent population is normal, it doesn't matter what size our sample is. N stands for sample size. It doesn't matter. Our sample distribution is also going to be normal. So if our parent population is normal, our sample sizes doesn't matter. What we're going to end up with, our distribution is a normal distribution. The only difference is when we calculate probabilities using the normal distribution curve, instead of calculating it with the standard deviation, we use something called the standard error, which takes into account the sample size. So we calculate the standard error with the standard deviation, and we divide by the square root of our sample size. So another thing that can happen is if our parent population is any shape. It could be any sort of distribution. It could be uniform. It could be skewed left. It could be skewed right. There's a whole bunch of, it could be bimodal. It doesn't matter. If we have sample sizes that are greater than or equal to 30, that means we have 30 or more objects in each sample, then our sample distribution is going to be approximately normal. Doesn't matter what the original shape was. We can use the normal distribution tools on it to calculate probability. And again, we are going to calculate standard error the same way. It's the standard deviation divided by the square root of our sample size. If our population is any shape and our that's a typo, and our sample size is less than 30, so any shape population, smaller sample size, we can't use the tools of normal distribution because we don't know what the shape is going to look like. So even if the population, the original population, is not normally distributed, the sample distributions of all our sample means will become normal the bigger our sample size gets. So if we're going to calculate a z-score or a standard score, if we calculate it from the population, we use the regular z formula. But if we have a sample that we're calculating a standard score for, we have to take into account the sample size. And so we use the standard error instead of the standard deviation. And that again is the standard deviation divided by the square root of our sample size. So when we calculate probability problems, if we're calculating from the population and it's normally distributed, Then we use normal CDF, lower boundary, upper boundary, mean, and standard deviation. That's what we've already been doing. And if we're using the central limit theorem and we're calculating from a sample, then we use normal CDF, lower boundary, upper boundary, mean, and then here is the difference. We use standard error instead of standard deviation. So let's try a problem. Based on tests of the Chevy Cobalt, engineers have found that the miles per gallon of highway driving are normally distributed with a mean of 32 miles per gallon and a standard deviation of 3.5 miles per gallon. If one car is randomly selected, find the probability that the car gets less than 30 miles per gallon. All right, so let's start out with our diagram. We have a mean of 32, so we'll put a 32 here, and a standard deviation of 3.5. That means this would be 35.5, this would be 39, this would be 28.5, and this bottom one here would be 25. We're looking for the probability that a car gets less than 30 miles per gallon. Well, 30 is going to be somewhere in here, and we're looking for less than, so that's going to be to the left. And when we calculate this, this is the same sort of problem we've been doing all along. N is equal to 1. So we're going to use normal CDF, and the lower boundary is going to be negative infinity because we're calculating to the left, and our upper boundary is 30. Our mean is 32, and our standard deviation is 3.5. And when I load all that into the calculator, I find that I get 0.2839. And that looks reasonable, about 28%. Okay. Same sort of problem we've been doing all along. This time, we have if 25 different cars are randomly selected and miles per gallon for each car is recorded, find the probability that the mean miles per gallon is less than 30 miles per gallon. So we're going to calculate for 30 miles per gallon, but if you look here, we have 25 cars randomly selected. That's a sample of 25. So instead of using standard deviation, we're going to use standard error, and that's going to be the standard deviation divided by the square root of our sample size. In this case, that's going to be 3.5 divided by the square root of 25, which is actually 5. So 3.5 divided by 5, that's going to give me 0.7. So the standard error is 0.7. So I'm going to go ahead and put that into the calculator. Normal CDF, negative infinity, because again, I am looking for the value from left to right, from negative infinity to 30. The mean is 32 still, but instead of standard deviation, we're going to use standard error. And I could put in 0.7 here, or if you want, you could do 3.5 divided by the square root of 25. And your calculator will do that all in one step within the normal CDF. So when I do that, I get 0.0021. Wow, that's a big difference from up here. Makes me feel like I've done something wrong. So why would these be so different? Well, if I'm going to set up the normal curve, and the mean is 32, and 0.7 is one standard error. That means that this would be 32.7, this would be 33.4. Down here I would have 31.3. Let's see, and here I would have 30.6. Less than 30 miles per gallon is going to be out here. And that's because when we calculate the standard error, we're dividing by our square root of our sample size, and that's going to pull these values in closer to each other. Because if you look here, 2 standard deviations away from the mean up here with a sample size of 1, 2 standard deviations, since 1 standard deviation is 3.5, 2 of those would be 7 miles per gallon. But down here, if I do 2 standard errors, then that's only going to be 1.4 miles per gallon. And 30 is less than 1.4 miles per gallon below 32. So this answer actually makes sense. All right, so I have one for you to try on your own. If you'd like, you can stop the video, give this a shot, and then restart it and check your answer. All right, second example. Assume that women's heights are normally distributed with a mean of 63.6 inches and a standard deviation of 2.5 inches. All right, let's set up our chart here. 63.6, 66.1, and 68.6. All right, and then 61.1 goes below, and the lower one is 58.6. All right, so 63 inches is going to be just to the left of the mean, and we want to be above, that's what it says, above, and it's one woman, so we should use the normal standard deviation. All right, let's go ahead and calculate that. Normal, we should have just above 50%. CDF, lower limit is going to be 63.6. Upper boundary is infinity. Our mean is 63.6, and one standard deviation is 2.5. By the way, if I wanted to take into account that I had a sample size of 1, I could do 2.5 divided by the square root of 1, which is 1, which happens to be 2.5. So we don't need to take it into account here when it's 1. So when I go ahead and calculate that, I get 0.5948. Okay, so now we're going to try if 100 women are randomly selected and the height for each woman is recorded, find the probability that the mean height is greater than 63 inches. So if we go ahead and calculate our standard error ahead of time, it's going to be the standard deviation divided by the square root of the sample size. Our standard deviation in this case is 2.5, and the square root of 100 is 10. So 2.5 divided by 10 gives me 0.25. I'm going to go ahead and put that in my calculator, normal CDF. Uh, 63 inches. Oh, up here, this is supposed to be 63. Sorry about that. All right, 63 inches, infinity. And then the mean is 63.6, and the standard error is 0.25. So if you wanted to predict what you were going to get, you might be surprised. But if we go ahead and set this up before, so we can see if what we get is reasonable, if our mean is 63.6 and one standard deviation is 0.25, then this will be 63.85. And the value above that will be 64.1. The value below will be 63.35. And the value below that will be 63.1. So if we're looking for everything greater than 63, that's lower than our two standard deviations away. And we're looking for everything greater, so that's almost that whole curve. So when I calculate it, I better get a fairly large value. And when I plug all of this into the calculator, I get 0.9918. All right, that's it for today.